Professor Salençon, Professor Wang, ladies and gentlemen, good afternoon. Thank you for coming to this Hong Kong IAS Distinguished Lecture Series. Today's speaker is Professor Jean Salençon, Honorary Professor at École Polytechnique and École Nationale des Ponts et Chaussées in France. He's a distinguished figure in the field of continuum mechanics. He also held the position of chair professor at large and a visiting distinguished professor at the City University of Hong Kong from 2011 to 2016. He's currently a senior fellow of the Hong Kong Institute for Advanced Study at CTU, and during his illustrious career, he served as the president of the French Academy of Sciences in 2009 and 2010, and the chair president over the Institut de France in 2009. Professor Salençon is a emeritus member of the French Academy of Technology and the Academia Europaea, and hold foreign membership in different institutions. He's also an honorary member of the Hungarian Academy of Sciences and a corresponding member of Académie des Sciences and Lettres de Montpellier in France, with a vast body of work that include 190 publications, 12 books, textbooks, and 8 multimedia software. Professor Jean Salençon is a renowned global leader in the field of continuum mechanics, contributing significantly to both theory and its practical applications. Without further ado, let's welcome Professor Salençon to give today's lecture.
Thank you, Professor Jianlu. Thank you, Jian, because we have known each other for many years. I don't know how many. Maybe you know, because at least more than 20 years, more than 23 years, something like that. Well, the problem with such a laudatory introduction is that people afterwards, after hearing the lecture, are a bit disappointed. So I hope we will not be too much disappointed after the lecture. Well, today, as a starting point, we are in Hong Kong. I invite you to go to France. And as tourists, we go to the Eiffel Tower. We look at the Eiffel Tower, you look at the 4 sides of the Eiffel Tower, and then you see that you can read 18 names on each side of French scholars. Gustave Eiffel wanted to honor 72 French scholars who had graced France during 1 century, because the Eiffel Tower was built for the 1st century of the French Revolution. Among those names, we find the name of Coulomb. Maybe you would notice if you were there, no name, no woman name. Well, but at the time, for instance, Sophie Germain could have been one, but maybe better known than only one. That's it. Okay, so now we are going to deal with Coulomb, and I want you to study with me what I call Coulomb's seminal contribution to soil mechanics. And you see the date is 1773. It's when this memoir called Essay by Coulomb was presented to the Academy of Sciences in Paris. 250th anniversary this year. A landmark test, all in construction engineering, but especially in soil mechanics. So I will concentrate on soil mechanics. This is a title in English. I highlighted some words, rules of maxima and minima and statics, because I believe those words describe the rationale to be developed in the memoir, they describe it perfectly. So, what about this memoir? It was presented to the Academy by Bossu. Maybe you never heard about this guy. He was an abbot and a mathematician. He had been Coulomb's former professor in mathematics, and he is known also for having edited and published Pascal's work in the book called Discours sur la vie et les ouvrages de Pascal. So this guy, Bossu, if you don't go to Coulomb, you don't hear about Bossu, but Bossu is an important person. Coulomb was a member of the French Academy afterwards. He was not, of course, when the memoir was presented. Where this memoir, you see, was written some years ago only for my own personal interest. That is what Coulomb pretends. Used in the many works I'm in charge of. Why? Why was he in charge of works? Because he was an officer, a capitaine en premier, an officer, in the Royal Corps of Engineers. And he has been in charge of building in Martinique, an island which is, I like very much, of course. He has been in charge of building a fort called Fort Bourbon. He spent 8 years in that island, and he returned from that island in 1772. And during that time, as he had to build walls, retaining walls, and so on, he made experiments, and so he wrote this memoir. And he says that he wanted to, as he says, the Academy always kindly welcomes the weakest attempt when it has utility as its object. This is an important word all along. So this is what we are going to go through. First of all, it is always important when you are looking to a scientific text to know the scientific context, the temporality. So Coulomb's memoir, here it is in the down here, Coulomb's memoir came after Galileo. Galileo Discorsi, 1638, with this famous problem of the cantilever beam, which is often considered as paving the way to the Hill design analysis. Of course, it came after Hooke's law has been discovered, ut tensio sic vis, it has been discovered. I would not say discovered, it has been revealed, because it was hidden. It has been revealed in 1678. But what is more important is to see before, that Coulomb's memoir came before. It came before Lagrange's work. The principle of virtual velocities had not been stated at the time. The concept of resisting forces had not been completely defined by Lagrange. It came 50 years before the concept of stress vector, stress tensor, and 100 years before the works by Tresca, a series of experiments about what Tresca called the fluidity of solids, those works are considered as the birth of the mathematical theory of plasticity. These are Coyte's own words. So this is the context. Now we start with looking at the memoir and what I call the first cornerstone in the memoir. It is the clear definition by Coulomb of resistance. He makes a distinction, fundamental distinction, between active forces. It takes the example of gravity force that always fully exerts its effect, and on the other side, coercive forces, we would call them now resisting forces. Those are only assessed through their limits. The resistance, one limit on one side, a limit on the other side, but you don't know the value in between. It can take any value in between. So this is very important. It's all the difference we have to take into account. Of course, it comes out from here that resistance for Coulomb comes from friction and cohesion. Friction. Friction refers to somebody called Amontons, who was a French scholar, and Amontons was the one who who stated the law of friction, which appears as this: the resistance due to friction is proportional to the pressure exerted. It means you have a force, a vertical force, for instance, acting here, pressure, then the horizontal force, which is resistance to friction, will be a part of this force, 1 over n, which now we call tangent phi. So I will use tangent phi instead of 1 over n. Cohesion. Cohesion, Coulomb refers to Van Musschenbroek. Van Musschenbroek was a scholar, a Dutch scholar from the Netherlands at the time, and he wrote in, you see, it's Latin. This was written in Latin, and what he says, cohesion is measured by the resistance solid bodies oppose to the direct disunity of their parts. What does it mean? You have particles of matter, and they have a cohesion, which means that they don't want to disunite one from the other. This is more or less exactly Galileo's statement. Galileo was speaking about a certain cement which held the parts glued together. See? Exactly. But notice that Coulomb never refers to Galileo. These are the only two persons Coulomb refers to in the memoir. Then with this, we have two components of the resistance. For Coulomb says there are additive contributions, two different phenomena, additive contributions. So we would say it is Van Musschenbroek plus Amontons. But as you see, I wrote, not yet Coulomb's law. You know Coulomb's law. Because Coulomb's law would only appear 8 years afterwards, in 1781, in another memoir presented to the Academy, and for which Coulomb was awarded a double prize. The Academy had offered a prize in 1779. Nobody won, so he obtained a double prize in 1781, and afterwards he was elected a member to the Academy. So far, so good. Now, this is the core of what we are concerned when dealing with soil mechanics. It's Coulomb's approach to what we call now active and passive thrust. The problem Coulomb is looking at, the solution he's looking for, is this one. It is the stability of a retaining wall. In fact, is concerned with the overall stability, but it distinguishes the stability due to the soil and then the overall stability of the wall. So what we are concerned with is only the part dealing with the soil. For this, he uses what we call a thought experiment, as Galileo did, if you look at the Discorsi. In this thought experiment, he delimits a solid triangle. These are his own words. That is subjected to gravity, that is subjected by a force, a horizontal force, acting at point F, and that is retained by a resistance that exerts along the line here, along the line AB. The fact is that, of course, it is a problem of equilibrium. Just have to work with equilibrium, those forces. But the fact is that when dealing with equilibrium and resistance, we know, because Coulomb told us before, that friction and cohesion are only assessed through the limits of resistance. So it is not a common problem of equilibrium where you know all the forces. The problem with some kind of indetermination because of the resistance. And we know that resistance resisting force can take any value between the limits. So I will look at the limits. And I say first, What the problem we are looking for is this one. We want to assess. Oh, I have to go back. It is this. It is because we have been there was voilà. We want to assess the value of the force that can be exerted at point F without causing the triangle to move either downwards, which is its tendency, or upwards. So you see, you are pushing, and you should not make the triangle, cause the triangle to move. Well, first, the force must prevent the triangle to flow downwards, from flowing downwards. Well, the minimum value for such a force that prevents solid from flowing downwards will be obtained when the resisting force is fully mobilized along this line and is directed upwards. Once you have said that, you obtain this minimum value as a function of angle phi here. Not alpha, sorry, angle alpha here. And, of course, A must be superior to A of alpha if we don't want this triangle to move downwards. But imagine that you are increasing force and tends to impulse the triangle upwards. Then it should not cause the triangle to move upwards. Then the maximum value for force A that does not cause the triangle to move upwards will be obtained when the resisting force is fully mobilized along this line as before, but downwards, and this gives us the other bound. So finally, we had A had to be superior to A of alpha, inferior to A prime. This is the statement by Coulomb himself. The force, without the causing to move, will lie between those two limits that depend on angle alpha. But if you want the bulk of soil to remain stable, this should be true for any triangle you choose, for any value of alpha. So, you will have to look at A of alpha is the lower bound, A prime is an upper bound. You will try to look for the maximum value of the lower bound and the minimum value of the upper bound. And so we are here dealing with the very title of the memoir. Remember rules, maxima, minima, statics. That all is said there. So this is what Coulomb writes. The limits where A will be a maximum and A prime a minimum. He states it very clearly. And to my personal and incomplete knowledge, of course, this is the first example of a reasoning that results in an optimization process. I don't think we have such example before, maybe, but I don't know. That's, I should say. Then, the case of what we call active thrust, minimization, Coulomb does it, and it is a lower bound estimate of the maximum pressure on the wall. What a lower bound? This is important. People sometimes do not know. Coulomb is aware that it is still a lower bound, even if he has done the maximization process. Why? That is what he says. Up to now, we have assumed that the surface that produces the maximum pressure was triangular. The simplicity of the results derived from this assumption, the easy practical applicability, remember utility, and the desire to be useful and accessible to the artist are the reasons why. The artists are not people who are painting or sculpting. No, the artists at the time were those people who were practicing what they call liberal arts. But If we would want to determine the curve that produces the maximum pressure in an exact way, here is, I think, the way it could be done. But here is the way. Consider now a non-triangular wedge, so we have a curve where you have to say to perform exactly the same reasoning. And the problem is with the resistance. It is no longer a straight line. So how can you do it? And here is the fact that Coulomb introduces what we would call now a slice method. It is the first introduction of a slice method. Here it is. You have those vertical slices, and since the problem is with the resisting force on GB, well, we will look here and consider those little tiny triangles here and there as wedges, tiny wedges which are supporting the weight of the column over them and are retained by the column on the other side. And recall that at the time the concept of stress vector was not available, so he could not do more than that. And the concept of stress vector is still in his mind. He does not know it, but he is doing that. Well, we stop here about that point. We complete with what is not in the memoir, which is about passive thrust. We minimize the maximum, the upper bound, and we obtain an upper bound estimate. So finally, may I sum up what we did? This is on the left-hand side, you have what Coulomb wrote, and I tried to illustrate it on the right-hand side. Imagine that A is force A, is a loading parameter. Imagine that the gravity force gamma is a loading parameter. We can draw this like that. You have a domain. In that domain, you have equilibrium and resistance are mathematically compatible. Outside, they are not. Active and passive thrust appear at that level. And what Coulomb did was having bounds on each side. So now what beyond Coulomb's analysis? First, we should retain some governing principles. I think the most important is this one, the clear distinction between the imposed loads, active loads, and resistances. Then, what Coulomb did is acknowledging as a necessary condition, not sufficient, necessary only, for stability. This necessary condition is compatibility between equilibrium and resistance. Then, 3 and 4, you obtain necessary conditions for the loads, and then you practice some kind of optimization process. What do you never heard of? There is no energy concept involved. You have noticed that. It's only a matter of statics under constraints. Well, after Coulomb, you know a lot of methods. You know them better than I do, sure. Fellinius slip circle method, 100 years ago. Renduli clock spiral, Taylor's 5 circles, slice method, and so on. And the problem with those methods is that they call for complementary assumptions, many of them, except for Renduli clock spiral, when phi is non-zero. Otherwise, the problem is not statically determinate, so you have to make the problem statically determinate, so you introduce complementary assumptions. Anyway, another idea could be, since we know about the principle of virtual works, would be to have a kind of kinematical or energy balance viewpoint. And the idea is when you want to check a global equilibrium equation, It is equivalent to write that the work by the driving forces can be balanced by the work by resisting forces. It is exactly... Oh, so where is the problem? The problem comes here. The work by resisting forces is not always well determined. When phi is 0, it works perfectly. But when phi is non-zero, it calls for complementary assumptions, by the way, the same as before. My director of thesis used to say, if you don't eat crude, you will eat cooked, but it's the same. It's the same food. Okay. Nevertheless, this was a kind of mathematical challenge at manual 1 century ago. This is an excerpt from the Compte Rendu de l'Académie des Sciences in 1922. I counted, I don't remember now, but maybe more or less 8 articles devoted to stability analysis of slopes and so on, even by a well-known mathematician. One is a well-known mathematician, is Émile Goursat, who is present here. You know Goursat's theorem. He was dealing with this problem. It was kind of a competition, trying to find a curve that, well, could make it possible. There was no solution that way. So how to come out of this problem, how to overcome this problem? We can do it through what I would call a theory of field design straightly derived from Coulomb's ideas. We start from the governing principles, and especially from the 2 first ones. Distinction between imposed load and resistances, and necessary condition. You take these 2, and you say that, well, any load for which these conditions are satisfied is a load for which compatibility is satisfied, and so it's a load for which stability is potential. In other way, let me say it the reverse. If this load doesn't belong to these two paragraphs, instability is certain. It is exactly what we obtained when we were dealing with Coulomb. We defined a domain of potential stability, which was this domain, this gray domain over there. It was the domain where equilibrium and resistance were mathematically compatible. In that place, there was, on one side, potential stability. You are not sure it is a necessary condition, it is only potential. But on the other side, instability is certain. It will collapse. You're sure it will collapse. If you want to have a drawing, more general drawing, we do it with some kind of this, and it is actually the same, but it is more general. Well, so having said this, how can we proceed? Well, there is a magic tool. The magic tool comes from the principle of virtual work, which is also the principle of virtual velocities stated by Lagrange. If you combine our 2 first paragraphs and the principle of virtual work, you obtain a statement which makes it possible to obtain that equilibrium and resistance are incompatible. What is the statement? Given a virtual collapse mechanism, so imagine a collapse mechanism, whatever it is, you call it virtual. Then you compute the virtual work by external forces. If it is superior to the maximum resisting work, then instability is certain. You should, at least 1, 2 of you should say, well, you just said a few minutes ago that we had a problem. So how is it solved now? Well, yes, of course. A few minutes ago I said this. The work, of course, the difference is here. We are not looking at the work by resisting forces. We are looking at the maximum resisting work. the maximum. And this one is the maximum value of the work that can be developed by resisting forces under the constraints we know. The maximum value under the constraints. This one doesn't call for any complementary assumptions. It is pure mathematics, and simple ones. It is unambiguously defined from the knowledge of the, I would say, the strength criterion, the resistance criterion of the material. As I said, no complementary assumption. And it is derived through a normality rule. Ha! Normality rule. What a shame. No. Normality rule is a mathematical rule. It is the optimality condition. Everybody who has worked a little bit about optimality with the convex knows that the optimum is obtained when the parameter, no, the variable, the test function is normal to the convex. This is the optimality rule. It's nothing to do with a constitutive law. We never heard of a constitutive law. And so, with this, we have this statement, which, as I stated before, virtual collapse mechanism, what can they say about them? Well, they can be completely counterintuitive. They don't have to be intuitive. They don't have to be realistic. They are just mathematical tools to check compatibility between equilibrium and resistance. So we don't have to say, oh no, this is not, it's a mathematical tool. And with this, be them counterintuitive, unrealistic, and so on. So, what they have to be efficient. Being efficient means that this value shall remain finite. And after that, you obtain, in the general case, a kinematical approach of the outside of the domain we are looking for. We are looking for the domain of potential stability, and we obtain the outside of it, and you try as much as you can to have more and more, you get more and more closer and closer to this domain. So, this is the end of the story of the theory of yield design. So far, so good. Well, what use is it? Well, first, just look at it with purely academical vision. Left-hand column, you find what you know, block mechanism, 1 or 2. You find also the famous method of characteristics, which was very popular when I started my thesis in 1964, far away, and with Sovkolovsky and so on in soil mechanics. Method of characteristics, it is purely what we have been describing just before. Second column, you see Brinchanson, a famous book by Brinchanson, I think it's 1963, where he imagined a lot of mechanism, virtual collapse mechanism. This works, this also is encompassed by the method. The two below here, I must say we have to take them keep them in mind. The first one is concerned with the bearing capacity of a strip footing under inclined and eccentric load. And below, the same problem studied by Alain Péquer and myself, the first one by Alain Péquer and myself, the second one by Alain Péquer, myself, and his student Kacharisis, the Greek guy, for a circular foundation. And on the right, the last column, there's recent work by Martin. Well, this is academic. Now, practice. Well, early in the 1990s, we produced a software. I say on the upper You see the laboratory, Laboratoire de mécanique des solides, et you see École nationale des ponts et chaussées. So it was an academic software we produced for the stability analysis of reinforced soils. S stands for soils or slopes, as you like. More or less 20 years after, TerraSol, the company TerraSol, produced version 4 of a software called Talon, where they introduced yield design calculation at last. Well, that is okay for now. In practice, it is interesting that to notice that theory leads to innovative methods, to innovative designs. This is first example is the Ryan and Tyrrell viaduct in Greece, which was completed in 2004. The foundation of this bridge were designed by Alain Pecker. I think that maybe it was in 2016, 2018, I don't remember exactly. Alain Pecker came here and delivered a lecture on this topic, complete lecture. So maybe you can find it on a website. So here is the design of the foundation. You have 65 meters of water. You are under severe seismic conditions and bad soil. So what Alain Pecker designed was to have all these columns there in the soil. Then up on the top, you had a gravel layer of 5 or 6 meters. Then you have this foundation. The foundation is 90 meters. 90 meters is, I think, more or less the length of a football playground, no? I think. Okay. So you imagine 5 of these. This is described. You can find it. You can also look at a movie. Well, it was okay to be used for this design. He first started with yield design analysis. Of course, he used also other methods to compare. You imagine that the checkers, when you have such an important such an important piece of work, you have checkers. You are allowed to check if you are right or not. So the checkers were there. He made also experiments, and here are the experiments, centrifuge experiments. Oh, I was working. Sorry about it. Centrifuge experiments to verify that the value he has computed were matched with the prediction, with the observed measured failure loads. Because you must remember one thing, that whatever its sophistication, any mathematical model is only valid insofar as its underlying hypotheses are verified. It may be wonderful if the hypotheses are not verified, you have to throw away the theory. Okay. So you have to verify it. So this was the innovation, completely innovative design. It was a precedent, and that is what Alain Pecker wrote recently. At the time of design, at the end of the 20th century, the design concept was completely innovative and required a lot of intellectual and financial investment to convince all involved parties. I remember I took part in some of these meetings. I was behind because I was not chartered, so I could not. And they were really looking at, is it worth? And he said, finally, the investment was worth it because this project paved the way for more recent ones. First of all, I have to say that this viaduct was subjected to a severe seismic event. I think it was in 2018. It was a 6.8 seismic event, and everything, it behaved as it was anticipated. And then, this was Smith bridge, you see that the principle of the foundation is quite the same. And another one. Seminal bridge, very recent, the principle is exactly the same. I'm pushing the wrong button. Okay. So, okay, this is good. Principle is exactly the same. In fact, some people, one of those who designed those bridges, were the checkers of the first one. So they knew exactly how it works, how they could be confident in it, so they could use it again. They say it plainly. So this brings me to a conclusion. Well, first of all, what shall we retain about Coulomb's memoir? Our 5 governing principles. You have seen, you know them. Essentially, the first one, essentially when you are dealing with reinforcement, you have to be completely clear when you have a reinforcement as to know if it is active or passive. It is completely different. And now, the legacy of 1773 and 1781 memoirs. What is the legacy? And now I will leave the floor to my colleague, Suzanne Lacasse. Suzanne Lacasse is a Canadian lady, Norwegian lady too. She was the former director of the Norwegian Geotechnical Institute, NGO, in Oslo. She's also a consultant here at GEO, and she delivered the lecture 2 months ago in Paris when we celebrated the 250th anniversary of the memoir. And so here is what she wrote. First of all, notice the coincidence. 250th anniversary coincides with the 100th anniversary of the principle of effective stress introduced by Terzaghi, and which was inspired by Coulomb's work. Second, she noticed that Coulomb mentioned the importance of including uncertainties in a safety evaluation. That is what we would call now reliability-based design. Third, you know that ULS, that is ultimate limit state, I usually say ULSD, ultimate limit state design, she said is based on the Coulomb principles. It is based, in fact, actually, on the theory of yield design. Is it what she says? The yield design approach is still the essence of a majority of design codes. So with this, we see what the legacy of Coulomb's memoir is. And she uses this French word envoi. And she says that the value of Coulomb's works lies not only in the discovery he made in the 18th century, but mainly in the developments to which the discovery led over the next years, which we have seen a little bit of. And with this, I thank you for your attention. Just in time.
Thank you, Professor Salençon, for this comprehensive lecture. So now the floor is open for discussion. Any question at this point? Yeah, Professor Wang.
I have a rather naive question. I think it's a statement you referred to several times. For example, on page 55.
Can we go back to page 55?
Yeah. So we talk about the limits of the fluid. For example, here, it says the limit of the horizontal force can be exerted without setting the fluid, which will lie between limits A and A prime, where A will be the maximum and A prime will be the minimum. It seems to me this is a obvious statement. I wonder if I missed something here. But later on, obviously, when you have the diagram, it shows something different. So I don't quite understand what exactly this was meant.
Well, this is exactly what Coulomb's right. This is the statement is comes directly from Coulomb. So I will say it that way. Maybe I've been too clear. When you read Coulomb's work, it is not so evident. This is always a problem. When you clarify the deduction, at the end it seems obvious. But when you read Coulomb's work, you have to go this way, that way, and so on. And maybe I shouldn't say that. When I was a student, I remember my own professor, venerable professor, he knew the answer, he knew the conclusion, but he gave the reasoning completely the reverse. Because it is quite tricky, you see. You have to take the maximum of a minimum, the minimum of a maximum, and he went the wrong way. So this is why I took it very carefully, but at the end, as you say, it's obvious. It's obvious. Yes. Yes.
Other question? Yeah, please. Yeah,
If anybody has question, press the button.
Thank you for your inspiring lecture. I focused I'm majored in geotechnical engineering, so this looks very familiar to me, and I like your presentation. And one question, because I focused on geohazard, for example, rainfall-induced landslides. In a slope, there are so many slip surfaces. So in the design of yield design, you need to prescribe a potential failure mechanism. So consider a slope. There are so many numerous failure mechanisms because each slip surface can be deemed as a failure mechanism. So you need to optimize, to search, to find some key failure mechanisms. So how do it becomes a system reliability problem? So
yes, this is what we first the first point we looked at when we made this STARS software, which was an academic software, but we considered slopes and with layers and so on. We had water, we reinforced slopes. And then using strictly the yield design approach without introducing anything else, we were looking for the best virtual collapse mechanism in order to obtain what we call a safety factor, which is not exactly a safety factor. It is what we should call more model factor or something like that, you see. But this is, you are quite right. You have to look for that, and so you need a software. And now what I think is important for us, because they were really reluctant to introduce it in their own software, is that Talleyrand finally decided to introduce it. Because when you use this theory, you can't say it stands, but you can always say it will collapse. And sometimes we said it will collapse when another software said, well, it stands. So they understood that it was necessary for them to have this kind of method to approach the problem. But since we are not working in mathematics, but working in geotechnics, we know that we always have to look at many methods and to have some methods that are what we call in French garde-fou. There is a word in English, something, rail or something like that, which prevents you from going too far away on one side and another side, which maintain you in the right way, you see. But your question is quite appropriate.
Other question? Yeah, I have some question. Yeah, so how to extend this Coulomb's law to extreme condition like earthquake or dynamic loading? Because when you build a bridge, you may have a wind or exceptional level of wind. And today, what's the engineering approach to take into account this in the design of a bridge?
Well, this is what was done, for instance, for Ryan and T-Ryan Bridge and for the other ones. It is a pseudo-static approach. This is the only thing we can do. Within this framework of the yield design theory, we use a pseudo-static approach. So we have this acceleration, for instance, it was for seismic conditions. You have the horizontal accelerations, gamma h, you have some kind of a percentage, and then we used it inside. This is how we did. We cannot, it is only pseudo-static. The only way we can work with it, yes. As far as wind is concerned, I am not aware of anything. Maybe it would be a problem to look at, yes. I never thought of it, yes. Maybe for my next 100 years, maybe.
Okay. Any other question? So if not, please.
Yes, please.
Yeah, please push the button.
I have another question. Because soil is a natural material, so about the soil strength, we don't know much about soil strength, or we take many samples, then the soil strength show some variability, and so we feel uncertain about the soil strength. So how do you determine the capacity or limit of a structure?
Yeah. So, if I understood well your question, problem is about the soil characteristics, the soil resistance, which how do you define it properly from experiments? I must say, surely you know it better than I do, you see. Yes. No, in such a... I've been working for so many years with Alain Péquer. We are working as a team, and he is in charge of this part. He could be able to answer your question. I must say I'm not able to answer it correctly. Okay. But you see, this is why I put what I call this caveat before, after this, saying theoretical models, wonderful one model, wonderful results, but you have to look at the underlying assumptions. If they are not satisfied, you can throw away your model, and that's it. But when we were in, I think I have a few minutes to, this is 2 months ago, more or less, we celebrated those 250th anniversary in Paris, and another, Patrick de Buan, who had been my, I would say, student first, and so on, collaborator, also gave a lecture on the topic. And he was dealing with slopes and reinforced slopes and so on. So very, very good lecture within the yield design approach. And I asked the question, do you have any experiments, anything to prove that what you have shown us, reinforced soil with columns, and the theory is true, is valid, you see, validation, yeah, validation is the word. And I should say, he didn't answer. And finally, the answer was on my right-hand side, was Alain Péquer had the answer, because he himself had done the experiments, and he knew how it worked, and when it worked, and when it didn't work. Remember, remember this curve, we had 4 points giving the results, and the line giving what was anticipated, and we were just on it. Otherwise, you would have thrown away the calculation, you see.
Yeah, another question. Yeah.
Okay, thank you. Thank you, Professor Salençon, for the very nice historical review of Coulomb's work, and also link to the Coulomb innovative application to the design of the bridge. And he's my student, so I try to supplement his question to clarify in ways that I think one of the assumptions that you just mentioned, the hypothesis under Coulomb's work, is that the soil is homogeneous. So everything behind the retaining wall everything is homogeneous. But this is obviously different from a lot of applications. The real soil, I think is what he's trying to mention, the variability or inhomogeneity. And could you share some thought how you want to extend the U design principle, if you want to consider this kind of inhomogeneity to somehow cater to the reality?
Yes. Well, first of all, we did it, what is quite rather easy, when you have layers, homogeneous layers, we did it, and take into account the slope and so on of the layers. This has been done in the computer software and so on. Another problem would be what we call probability yield design, probabilistic approach. This is one chapter of the book I wrote after I had given the lectures here in CTU during 3 years. I gave lectures on yield design analysis, and there is a special chapter devoted to that point, showing how we can work with probabilistic approach either on the loads or on matter, the material. Of course, it is not a marvelous tool, but it gives idea, it gives some ways to work. From a mathematical viewpoint, it's okay, but as I said, mathematics is one thing, and then you have to work with it, it is different. And also there is another point, in the same book, another chapter is devoted to ULSD, ultimate limit state design, based upon yield design, and showing what the different coefficients we use in ULSD. We have coefficients on any parameter and so on, and finally a global coefficient, how you can clarify that point through a yield design approach. So those are devoted to this, such things. Yes. But how can we? The problem is always to describe heterogeneity of a soil. Some kind of a distribution, something. We can do it. If you know the distribution, I may say, if you can describe it, you could do it, but you can't describe it precisely. Yeah.
Any other question? Yeah, I have another, not a
Go
question,
on.
comment. Another type of bridge designer is our dentist. They need to make decision with heterogeneous soil. Yeah. Then they take 5 minutes to design what's the size of the bridge, what's the material they need to use. So have you checked if there are some similarity? Because I know they have some rule. Someone have derived some rule for the dentist. They always apply this rule, but I don't know if that comes from the practice or that comes from some theory.
I don't know. I will ask my dentist. Yeah. Yes, because he has a machine, Fab Lab for himself. He invited me to visit, so I will ask my dentist. You see, it's a problem. What is good with Jean-Loup is when you discuss with him, you always go back to your house with a lot of new ideas. So that is what you get from him.
Because I'm surprised they are very strong, and the failure rate is quite low. Because when the dentist decide how to, of course, probably is over-designed. So it's
but I think the problem will come with this the way they are making them now. That they wish to diminish yes. Well.
Yeah. Okay.
So good question about bridges and bridges.
Okay, so let's thank again Professor Salençon.
Thank you all. Thank you.
Thank you. We are very honored to have Professor Salençon deliver such an insightful lecture. And this lecture has a special meaning because it holds the final public lecture by Professor Salençon. Let's express our sincere gratitude to Professor Salençon once more. Thank you.
Thank you.